Okay, let's go over section 2.8 in this video. Before moving on 2.8, let's recall about 2.7. We know that the slope of the tangent line is the limit of f a plus h minus f of a over h when h approaches 0. That means the 2 point a and a plus h is very close to each other because h now getting smaller to 0, and when h is approaching 0, then this a plus h will be approximately equal to f of a, which is very close to f of a. So that means we are trying to find the limit when the 2 points are getting close to each other. Now the concept for the average velocity is very similar. So we already know that the average velocity is going to equal to the displacement over the time, right? So the velocity is the displacement over the time. Now if I have, consider I have, this is point A, right? This is point A plus h. So if you are here, then we are at point A, then we add h unit, we get to a plus h, which is this second point. Now the displacement is just, this is the function f. So the displacement is just the function at the second point, which is a plus h, minus the first point is f of a, and then over the distance between them, which is h. So this whole thing of the limits is really the displacement over the time. And when h is going to 0, that means this distance becomes smaller and smaller, or a plus h is getting closer to a. So we are trying to find the slope of the tangent line at only one point, and that point is point A. So the same thing here. When we let h go to 0 or approaching 0, we are finding the average velocity of 2 points. One point, the first point is a, the second point is a plus h, very close to a. And when a plus h is getting very close to a, eventually we are just finding the velocity as point A. So if we include the limit to this displacement over the time when h goes to 0, then we are finding the velocity or the instantaneous velocity when at point A. Okay, so if we write as v of a, or the velocity as point A, this is the limit when h go to 0 of f, this whole thing, minus f of a over h. So this second point A is the velocity at that point. So if you look at this function, this whole quotient here, this point is the point that we are actually finding the velocity at that point A only. Okay, and this is also called the derivative at A. Okay, so the derivative at A is actually the limit of the tangent line problem. Now recall that we already know that if we have a quotient delta y over delta x, this is called the rate of change, right? Which is the slope, or y2 minus y1, the change in y, x2 minus x1, the change in x. So delta y over delta x is the rate of change. Now the instantaneous rate of change the instantaneous rate of change, we apply the same concept here. So the instantaneous rate of change is actually just the limit when delta x approaches 0 of delta y over delta x quotient here. So the same definition. Oh, sorry. Let's go back here. Okay. Sorry. Okay, let's go back here. So the instantaneous rate of change is the limit of the quotient delta y over delta x when delta x approaches 0, and that is the same thing at the limit of x2 go to x1. So remember here, if I call this is y of x function, for example, I call this is x1, this is x2, right? So delta y over delta x equal y2 minus y1 over x2 minus x1. So when delta x approaches 0, that means x2 and x1, they are very close to each other. Or x2 is approaching to the value of x1, so that x1 minus x1 becomes 0. Okay, so that limits become limit of x2 go to x1, and the output is fx2 minus fx1, or the change in y, and the change in the x is x2 minus x1. And this is similarly so this factor is the same thing as the one that we talked earlier about the instantaneous velocity, or we are just finding the derivative as the point x1. So the function that you are subtracting on the right side is the point that we are actually finding the derivative at that point. Okay, so we can conclude that f prime of a, if we have the derivative at that's one point a, this is called the instantaneous rate of change of the function f of x with respect to x when x equal a. So when I write f prime of a, that means I'm talking about the instantaneous rate of change, or the derivative of f of x with respect to x when the value of x now is at point a. So that is the summary of section 2.7. Now let's go on to section 2.8. So we take the same concept here. So if I write limit, whenever I write f prime of a, that means I'm talking about the limit when h go to 0, f of a plus h minus f of a. So the second point here, we are subtracting from this point. A here is the one that we are trying to find the derivative at that point here, over h. So you must remember this formula. This is always true. Okay. But now, instead of letting the point a, we can talk this function in general of f prime of x. So instead of writing a, now we write x. So h go to 0, f of x plus h minus f of x over h. So f prime of x, or the derivative of x, is the limit of these fractions. Now, what are the derivatives tell you? So if I have a function, something like this. Okay, so remember, the derivative or f prime of x is the rate of change, or you can think of the slope at that point. Okay, so remember, if I want to find the derivative of this function at this point, so remember, the derivative is the slope at that point. So if I find the slope or the slope of the tangent line at that point, I can draw the slope here at that point, the tangent line to this point. Now, if this tangent line is horizontal, that means the slope is 0, or the derivative at this point is 0. The same thing is true here. If I draw the tangent line to this point, I have constant tangent line or horizontal, or the derivative at this point is 0. What happens if I want to find the slope at this point? So I have to draw the tangent line. So the tangent line to this point is this line, and this line, remember, it is not horizontal, but it's a linear function, and look like it's increasing, right? It's increasing, so it's going up. Or you can say that the derivative at this point is bigger than 0. What happens if I have this point here, and I can draw the tangent line to this point, and this seems like the function or the slope or the tangent line here is decreasing, or you can say that the derivative at this point is less than 0. So the derivative is the slope at that point, or the rate of change at that point only. And you can draw the tangent line at that point, estimate the slope, and you can see whether it is positive or negative or 0. Now we learn about the derivative. So it's required that we know how to take the derivative of a given function. So what if I am given f of x equal x to the cube minus 3? I mean minus x. Now I have this function, and the question is asking me to find f prime of x, or the derivative of x. So how do I find it? So remember, from previous slides, we know that f prime of x is the limit when h approaches 0 of f x plus h minus f of x over h. Okay, so that's easy. We have the formula, so we just have to plug in everything. So let's rewrite the limit here, h go to 0. Now f of x plus h, so this is a composite function. They give us the function f of x equal this thing. Now we want to find f of x plus h. So whenever you see the x here, just grab this whole thing and plug in, because we already have a function f, right? So x plus h, just grab the whole thing here, plug into the x. So x to the cube, now grab the whole thing, which is x plus h to the cube, minus, and then you see x again, grab the whole thing, plug that in. Okay, subtract, rewrite that down. F of x, for f of x, this is the same thing as the given function, so we don't have to change anything, right? So grab the whole thing, bring it down, and then over h. Okay, so we need to expand this out. So how do I expand this out? So remember the formula. I have a plus b to the cube. This is equal to a cube plus 3a squared b plus 3ab squared, and then plus the last one to the cube. Okay, so rewrite the limit here. So x, the first one to the cube, plus 3 times the first one square multiply with the second one, and plus 3 times the first one, the second one square, and plus the second one cube. Minus, so expand this parentheses out, so minus x and then minus h. The same thing here, bring the negative to inside, so minus x cubed, minus and minus become plus x and over h. Okay, so again rewrite the limit h equal to 0. Now let's try to simplify this expression. So plus x minus x is gone. Okay, what else? Okay, so x to the third power minus x to the third power, subtract them, it's order, so it's gone too. So we have 3x squared h plus 3x h squared plus h cubed minus h over h. So remember, we want h to go to 0. So the first, because we have h at the bottom, so when you plug h equals 0, then we are dividing by 0, which is undefined. So we don't want this to happen. So we have to factor out the h on the top in order to cancel with the h at the bottom first. So let's factor out the h on the top. So factor out the h, 3x squared, and then plus 3x h, right? Take out one h to the outside, and then plus h squared, and then we take h, have one left, and h. Oh, don't forget about the limit here. So now h and h is gone. We have the limit of h go to 0 of 3x squared plus 3x h plus h squared minus 1. Now when h go to 0, that means we are plugging in h equals 0 to this whole expression. So when h equal to 0, this term is gone. This term is gone, right? We already have these two left, these two factor, which is 3x squared minus 1. So that is our answer to this problem, and this is the f prime of x. Okay, so follow this formula, plug in everything in this format, simplify the algebra, and you should get the answer. Okay, let's try another problem. Okay, so now if I have f of x is the radical of x, now phi f prime of x, and then state the domain of f prime of x. So the problem is very similar. F prime of x is a limit when h go to 0, f of x plus h minus f of x over h. Now write out the limit again. F of x plus h, so we have the function f of x, so x plus h now is in the place of x, right? So take this radical x, you take this whole thing, plug in, and then minus f of x, which is this thing, we already have it, over h. Okay, now the question is, how do we simplify this in order to cancel the h at the bottom, so that we are not dividing by 0 when we plug in h equal to 0 to this limit? So the solution is because we cannot further reduce this one as compared to the last example, but we have something with the radical, two radicals subtract each other, then there's a trick to this problem that you have to multiply by the conjugate of this one in order to simplify this one. So if I have x plus h minus x over h, so in order to simplify this type of a problem when we have two square root and then subtracting each other, the problem is you have to multiply by its conjugate. So the conjugate of this problem is consider for the top. The conjugate of the top is the same thing at the top, but the minus sign becomes the plus sign. So that is the conjugate of the top. Now, if you multiply this whole thing, make sure you divide that the same amount of the factors, because these two divide each other give you 1. So you multiply by 1, which is the same thing as your original function. So nothing is changing. So multiplying the top by its conjugate, so the minus sign becomes the plus. This thing is the conjugate of this one. So remember, if I have, this is the sign note, if I have square root of a plus square root of b, then the conjugate of this whole thing is square root of a, and the plus sign in between become the minus sign. So remember this conjugate properties. So I take the conjugate on the top and multiply to that and divide the same thing at the bottom. Now we can simplify it. And the reason we use the conjugate property, because remember the difference of the square. A square minus b square equal a minus b multiplied with a plus b. Now we have a minus b multiplied with a plus b, which is this property here. So we can get them back to a square minus b square, right? So a is this one, b is this one, a minus b multiply with a plus b, which is this formula here. So this whole thing becomes a square minus b square. A is this one. When you square this one, the square root is gone. So a minus b, which is this one, when you square, the square root is also gone. So on the top, you have this now. On the bottom, you have h, and then multiply with this one. X plus h plus square root of x. Alright, so now let's simplify more. Write a limit here. H still go to 0. So x minus x is gone. Only have h on the top. And on the bottom, you still have the same thing. But now you see, we have h and h, top and bottom. So we can cancel them, right? So that gives us 1 on the top. On the bottom, we have x plus h plus square root of x. And now you can plug in h equal to 0 to this whole expression. So when you take the limit, just plug in h equal to 0 to this whole thing. So x plus 0 plus square root of x. So this whole thing gives you 1 over square root of x plus square root of x, or 1 over 2 square root of x. Okay, so that is the f prime, the answer for f prime of x. Now we have f prime of x equal 1 over 2 square root of x, and we want to find the domain for this function. So remember, the domain is all the possible value of the x that make this function defined. So you want to find the value of x that make this function defined. So remember, because x now is inside the radical, and for the radical, we only take the value from 0 to positive infinity. You cannot have negative value for x inside the radical, right? And then one more thing, if you have the 0 for x, now square root of 0 gives you 0, then 0 times 2 is 0, then 1 divided by 0, which is undefined. So anything bigger than 0 up to positive infinity should be the domain of this function. So the domain now is 0 and up to positive infinity, because you can have 0. 0, if you plug in here, 1 divided by 0, which is undefined. So anything positive and bigger than 0 is the domain of this particular function. Okay, let's go to the next one, the next topic. So when we talk about the derivative of the function, we usually write f prime of x, but if we're not writing this notation, we can also write y prime. So y prime is also the notation for the derivative of the function f, or you can write dy over dx. That means this is the derivative of the function y with respect to x, dy over dx. And or you can say df over dx, or the derivative of the function f with respect to x, or you can write d over dx and then f of x. So we take the derivative of the function f with respect to x, or you can write the big letter D and then f of x. We take the derivative of the function f. So there are many different ways to write the notation, but usually we use this one, f prime of x, y prime or dy over dx, or d over dx, f of x, as the notation for taking the derivative. Now remember, used before we have something called f prime of a. That means we are trying to take the derivative of the function f as the point x equal a. So this is the same thing as we are taking the derivative of the function y or f with respect to x when the value of x equal to a. So if I write this notation, when x equal a, I mean that I take the derivative of the function f or y at the point x equal a. Alright, so let's move on. We have one theorem in this section. So the theorem states that the function f is differentiable at the point a if f of a exists. So if I ask you, is the function f differentiable? If I ask you that if the function f is differentiable or not, then make sure that f prime of a, or the derivative of a of the function f at point a exists. So let's go over one example. I have the function f of x equal the absolute value function. Now the question asked is, where is the function differentiable? So where is the function differentiable given the function f of x equal x? Okay, so we need to find out where this function that we can take the derivative. Okay, because this is the function of the absolute value, we have three cases to consider. The first case is when x less than 0, x equal to 0, or x bigger than 0. Right? Now let's take this case first. So for x bigger than 0, so if x bigger than 0, then the function f becomes just x, right? We can drop down the absolute value side. Now let's try to find, for this case, let's try to find the derivative of the function f and see what do we get from there, and to check if the derivative exists or not. Okay, so let's find the derivative of f of x for this case. Remember the derivative from previous slices. H go to 0, f of x plus h minus f of x over h. So this is the same thing as the limits go to 0, f of x plus h. Now because x is bigger than 0, we have this function. So x plus h, you wrap this whole thing, plug into x. Right? Remember we find the limit before. Subtract f of x, which is this one, already we have it, right? Over h. So x and h, x and x are gone. We have limit of h go to 0 for h over h, or just 1, right? And the limit of a number is just that number, so 1. So that means when the case x bigger than 0, the limit, the derivative of the function f is 1. So we have the limit there exists. So let's check for the second case. For x less than 0. Now, when x is less than 0, f of x become minus x, right? Because of the absolute value. Now, let's check the derivative for this case. Again, limit when h go to 0, f of x plus h minus f of x over h, and this is equal to the limit when h go to 0. So f of x plus h, right? We have the function f is here, which is minus x. So wrap this whole thing, plug into the place of x. So minus of x plus h, right? And then it's minus f of x, which is this guy. So f of x is minus x here over h. So the limit when h go to 0. So let's try to simplify this expression. Minus x, bring the minus 2 inside, and then plus x here, x. So limit when h go to 0, again plus x minus x gone, minus h over x. Limit of h go to 0, this become minus 1, and the limit of any number is just that number. So minus 1. Okay, we have the derivative for the case x less than 0. It is defined, which is minus 1. And for the case x bigger than 0, we also have the derivative of that function, which is 1. And that is defined. Now the last point we want to check is when x equal to 0, and check if the derivative exists or not. So let's go to the next slide. We're gonna check at that point and see if we can able to find the derivative or not. So for x equal to 0, so we want to find f prime of x. So this is the limit x go to 0, f of x plus h. Because x now is just equal to 0, we can just simply write x equal to 0 and plug in 0 in here, minus f of x, which is 0, over h. Now this will become the limit when h equal to 0, and remember this function we are given with this function. Now f of 0 plus h is just h, right? So we can f of x or f of h, so plug in h in the place of x, which is absolute value of h, minus f of 0, which is just 0, and then over h. Okay, so really we just have the limit of h go to 0 of h over h. Okay, we cannot drop the absolute value because when h go to 0, there are two cases. If the first case, if the limit when h go from the right of 0, which is something on the right of 0, then this thing become a positive h, and we're gonna have the limit of h equal to 0 on the right side of h. We can drop the absolute value now, because if we go from the positive side of the 0, then this whole thing will become a positive h, or we have the limit of 1, which is 1 for any number. However, if we go from the limit from the left of 0, now when you drop the absolute value, it's gonna become negative h over h, which is the limit when h equal to 0 on the left side of minus 1 or minus 1. Because the limits on the left and the limit on the right, they are not matching each other. That means the limit, the derivative, this whole thing is actually the derivative when x equal to 0, but the derivative on the left side and the right side are not equal. So the derivative at the point x equal to 0 does not exist. So therefore, we don't have a derivative at this point when x equal to 0, or it is not differentiable as x equal a. Or 0. Alright, so let's move on to the next theorem. Okay, so we have another theorem, and it states that if f is differentiable as the point a, then f is continuous at a. So basically, let's take a look over this theorem. We have a function f, and if f is differentiable at a, that means we can take any derivative at all the points of that function. Then that means that function is continuous at all the points. Okay, let's say that again one more time. For function f, if we can take the derivative of this function at any point a on the domain of that function, then this whole function is continuous at all the points. Does that make sense? Okay, let's go. How about if we reverse this statement? What if f is continuous? Does this mean that this function is differentiable? No. So make sure you know the reverse of this theorem is not true. And remember, from the previous example, we have f of x equal this absolute value, and this absolute value has the curve, I mean the wrap of this one. Now we already discussed that as the point 0 here. At this point the function is not differentiable, right? So the question is that if f is differentiable, then f is continuous. Then f is continuous at a, right? How about if f is continuous at a? Does that mean that the function is differentiable? Remember, at this point 0, we cannot take the derivative, or f is not differentiable at a. And because f is not differentiable at a, we cannot say anything about the continuous at this point. Unless the whole thing is differentiable, then we can say that the function is continuous from this theorem. Now, if f is continuous, if we reverse that, if f is continuous, then this function is differentiable. That is not true. If we take a look at this example, this whole function is continuous, but it turns out that at this point it is not differentiable. So if you take the reverse of this theorem, it is not true for some cases. So make sure it's only go on one way. If the function is differentiable, or you can take the derivative of that function at any point, then that function must be continuous at all the points that you can take the derivative. Alright, so let's I'll show you a few pictures where we have the following case for differentiable. Okay, so the only time that we cannot take the derivative or the function is not differentiable is when we have the corner of the function. So you see here we have a corner. That means we go this way and then we go up. If we have a sharp corner, so if we have a sharp corner like this one, then at this corner we don't have the derivative, or it is not differentiable. Okay, or in the function of discontinuous, if the function is not continuous, then of course the function is not differentiable. And the last case is if the graph is something like this. If you want to take the derivative at this point, if you draw the tangent line at this point, and if we have the vertical tangent line, then we don't have the derivative at this point, or the function is not differentiable. So in the case of vertical tangent line or discontinuous or the sharp corner, then all of these cases we don't have the derivative for the function. Alright, so let's discuss one more topic, then we end up this section. So this last one is the higher derivative. So remember, f prime of x is the derivative of the function f, or you can call that this is the first derivative. Now if we take the derivative of this function, or we take the derivative of the derivative, it will become the second derivative. So if we take the derivative one more prime, it will give you double prime of x, or f double prime of x, or the second derivative of the function. Okay, and the same notation, we instead of writing dy over dx, now you can have d square y over dx square. Remember, d represents for the derivative, so the second derivative, the 2 has to go with d, and with respect to x, we have to write the 2 on the variable x, or you can write y double prime f double prime, something like that. Now one example. Okay, I have the function f of x equal 2x squared. Actually no, 2x, yes, 2x squared, and I want to find f double prime of x. Okay, so let's try to find f double prime of x. Now, in order to find f double prime or the second derivative, we must first find f of x and then take the derivative out of this function one more time. Now, the derivative is what? It's always the limit when h approaches 0, f of x plus h minus f of x over h equal the limit when h go to 0. F of x plus h, we have the function f, so wrap this whole thing in the place of x. 2 of x plus h squared minus the function f, which is here, 2x squared over h, and this is the limit of h go to 0. So for this one, you have to expand out the square of this factor. So x squared plus 2 times xh plus x squared minus 2x squared over h. And again, try to simplify this. Multiply the 2 inside, 2x squared plus 4xh plus 2h squared minus 2x squared over h. Now 2x squared minus 2x squared is gone, right? Cancel its order, and we have what? 4xh plus 2x squared over h, and this is the limit when h go to 0. We must try to cancel the h at the bottom so we can plug in h equal to 0, and we're not dividing by 0. Okay, so first try to factor out the h on the top, and if we do that, we have 4x plus 2h over h, and that's gone here. Let's give you limit when h equal to 0 of 4x plus 2h. Now we can plug in 0 for h, and if you plug in, this is gone, and you have 4x as your first derivative. So 4x is your first derivative. Now we have the first derivative being 4x. We are trying to find the second one. The question asks us for the second one. So now we take the second one is basically just the derivative of the first one, right? So this is the limit when h equal to 0. Again, the same thing. If you take the derivative, always take the limit of h equal to 0. F now become f prime because we are taking the derivative with respect to the first derivative. So x plus h minus f prime of x over h, and this is going to be equal to limit h equal to 0. F prime is here, which is 4x. So x plus x, wrap this whole thing, plug into x. So 4x plus h minus f prime is 4x, right? This here, over h equal to limit h equal to 0, 4x plus 4h minus 4x over h. 4x are gone, right? So give you the limit when h equal to 0, 4h over h. Now cancel the h, give you limit of h go to 0 of 4, and the limit of any constant, any number, is just the number. So 4 is the second derivative of the function f of x. Alright, so again, we can have the third derivative, the fourth one, and the same thing. You can write the notation as d squared for the second one, write df dx, and d cubed for the third derivative, or the 4 for the 4 derivative, or f prime, f double prime, f triple prime, or when we get to 4, we no longer using the prime, but we have to write a 4 inside a small parenthesis. Okay, 4 and above. Okay, so there's one last thing I want to mention. Remember the problem of the velocity. If we are given a function s of t as the displacement or the location function of the object. Now, if you take the derivative of this function, the displacement, right, location function, if you take the derivative of this function, we will have the velocity function of that particular object. And then if we take one more derivative, or the second derivative, you're gonna have the acceleration. So I want you to remember this one very carefully. The displacement or the position function, if we take the velocity, the first derivative, you get the velocity. If you take one more, the second derivative, you get the acceleration. So make sure that you can memorize this stuff. Okay, so that is the end of section 2.8. Now I want to get you guys the extra credit, okay, for the upcoming first midterm exam. So if you finish watching this lecture video before the class on Monday, then please email me. So email me and include your name and say that you watched the lecture video for 2.8 on on Canvas, and just give me the course, which is section 2.8, right? So just say that the code is section 2.8 and your name, and say that you watched the video before Monday, before the class on Monday. If you send me an email and say the course, which is section 2.8, your name, and indicate that you watched the video, I give you 5 points extra credit toward your first exam. So it's only apply for now, from now until before the class on Monday. Make sure that I get your email. Alright, thank you.